enjoy the Christmas holiday and that you are ready for the new sessions of Journal Club. Today we have Tiziano Labruna as a speaker. Just a few words about Tiziano before we start. So Tiziano got his bachelor and master degree in digital humanities from University of Pisa, focusing on computational linguistics and topics related to artificial intelligence. Then in 2020, he started a PhD with the Free University of Brooklyn and in collaboration with Fondazione Bruno Kessler, where he works with the natural language processing research unit under the supervision of Professor Bernardo Magnini. And today, he will give us a talk of the title Impact of Domain Change on Task-Oriented Dialogue System. So I think that we can start. So Tiziano, my brother, when you are ready, you can start.
Thank you, Gianluca, my brother, for the introduction. So the topic of my PhD is dialogue systems, and in particular, I'm focusing on analyzing the impact that domain changes, that is changes that occur to the world, have on task-oriented dialogue systems. So the first thing we are going to see what is a task-oriented dialogue system. So let's say that we have a user and a system. Let's say that the user says something like, I want to find a restaurant in the center, and the system responds with information about this request. So a task-oriented dialogue system has the objective of guiding the user through reaching a certain goal. This goal can be booking a restaurant or buying a train ticket or a room in a hotel. So let's go a little bit more into the details. This is the general flow of how dialogue system works. So we have a user sending a message. Once the user sends a message, we have three components that manage this message in order to give the answer back. These components work as a pipeline, so one after the other. The first one is dialogue tracking. The DSC component is responsible for keeping track of the conversation. So it needs to extract the information from the message and to remember the information during the conversation. Then this information is passed to the dialogue policy component. This component has to find the best action to be returned to the user. And finally, the natural language generation is responsible for transforming this action into a message that can be read by the user that needs to be returned to the user. Each one of these components is based on a model, machine learning, deep learning model. And these models, as every machine learning model, needs some training data. And in our case, training data is a conversational data set. So the one I call training dialogues. So simply a collection of a conversation between a user and system. In order to create this data set, we need an expert or a crowd, a bunch of people that need to collect this conversation. And this is done in different ways. The most popular is the one called the Wizard of Oz, where we have a user playing the role of so a person playing the role of a user and another person playing the role of a system. Anyway, these are manual ways of creating the data set. You can understand that are very costly. So this is an example of a conversational data set. As I said, a simple interaction between user and system. Another thing is the domain knowledge base. So we assume that every conversational data set is consistent with some domain knowledge base. This is basically the information of the world. It can be a collection of restaurants, for example. And each restaurant has its own properties, for example, name, food, and price. Let's give a couple of labels. So on the left part, we have what we call the slot name. And on the right part, what we call the slot value. As you can see, the slot values are also present in the dialogue, in the conversational dataset, and they can be about everything. Here we have a name for the price, but it depends on the information we are interested on. Okay, then the single restaurant, we call it an instance, and the collection of all instances is called concept. So we could have a concept of restaurants, but we could have also a concept of hotels, trains, depending on what is relevant for our domain. So this is the general functioning of a dialogue system. What I'm interested about this is to consider the situation where there are some changes. There can be different types of changes. We can have changes of slot values. For example, a restaurant start to serve a different type of food, or we can have a different slot name. So if we are not interested anymore about the area of the restaurant, but we are interested about whether it has internet or not. For example. We can have a change in the instances. A restaurant closed down and another one opens up. Or a change in concept. So we are not interested anymore about restaurants, and now we are interested about the hotel. Okay, so what happens where there are some of these changes? So I'm marking the changes in red. So now we have a new domain knowledge base. So the word change, this knowledge base contains different information. And accordingly to this, also the user wants to know different information. Maybe there is a new restaurant, and the user wants to know information about this new restaurant. Okay, so how do we deal with this situation? If we have the old dialogues, it's impossible to build a model that is able to give the proper responses to the user. We actually did some demonstration to show that this problem exists. So here, this is on the dialogue state tracking component. We are bringing different amount of changes from 25% to 100%, because all the slot values changed. And we are seeing that when we increase the amount of changes, the performances of the models, we experimented with the two different DXT models, trade and Tripy, so the performance decreases. The same happens with the dialogue policy component. However, here we consider two different experiments, one when we add new instances and one when we remove instances. We can see that when we remove instances, it doesn't bring so much impact, because we are removing some instances, but all the other are there. So the user keeps making questions about the references that are there, on which we already know the answers. But in general, so we can see that when there are some changes, the performance of the models decrease. So how can we deal with this situation? The most simple answer is to create new training dialogues. So you need to ask an expert or the crowd to collect new dialogues from scratch. But as you can imagine, this is a very costly solution, because every time there is a change, you need to recreate from scratch all the data set manually. And so an alternative to this, which is our solution, is to do the same thing but in an automatic way. So we call this dialogue adaptation, and dialogue adaptation means creating new training dialogues that are consistent with the new domain knowledge base, with the new situation, in an automatic way. So here we can see an example. So on the left part, there is the initial situation, the original knowledge base, and in the right part, there is the new situation. So first we have this restaurant called Off Bistro, and there is a user asking about the restaurant that sells British food, and the system says that there are three restaurants, and it advises the user with the Off Bistro. Then on the right part, the office row doesn't exist anymore. The restaurant goes down. And now we have a new restaurant that says Poke House. So when the domain knowledge base has changed, we also need to reflect those changes in the dialog. So we need to make some changes also in the dialog. So as you can see now, we have Poke instead of British, one instead of three. So this operation looks very simple, but actually there are many things to consider when you do this. For example, when you substitute 1 to 3, you need to also consider the context of the sentence. Because now you don't have, you can't keep different options, so you need to change it to option. And also, one needs to be consistent with what you have in the knowledge base. Before you had 3 British restaurants, now you have 1 Poke. So, okay, many things to consider. This is a little bit more formal way of saying the same thing. So, dialogue adaptation means modifying a task-oriented dialogue that we call D0, that is consistent to a knowledge base AB0, in order to produce new dialogue D1 that are consistent to AB1. And as I said, there are some things to consider. So we want to maintain dialogue coherence. When you say something in a certain point of the conversation, it needs to be consistent with what you say in another part of the conversation. We want to preserve domain appearance. So what you say needs to be consistent with the knowledge base. Another desirable thing is to maintain linguistic variability, because people don't always use the same words when they express themselves. So the slot values, it's better if sometimes they are in one version, sometimes in another version. And as I said, we need to respect morphosyntactic constraints. So the sentence needs to be grammatical. So let's see some approach of actually implement dialogue adaptation. So let's consider a sentence from dialogue source, so the initial situation. So for example, I'm looking for a British food restaurant. So let's say that British is not relevant to our new domain. Sorry. So we want to change British into another slot value that is relevant to our domain. So first of all, we mask the word with the slot name, and then we need to find the best word to be substituted to the mask. There are different strategies. I listed some of them, and now we're going to see them one by one. So the first one is the most simple. It is this means simply looking into our knowledge base target, so in the new situation, and the information regarding the new situation, and just selecting one value with the same slot name that we find in the sentence. So we take one food from the new domain. And we can say that this knowledge base target is about restaurants in Trento. And so we select the slot value of Trentino food. So this has the advantage of being a controlled environment, because you need to set some rules for doing this, so you know what you're doing, and it's a relatively easy design. But as you know, every time that you do something by rules, it means that you can't cover it all. So the rules are limited. So everything you define by these rules is covered, but everything else, there will be always something that it's not covered. Also, there are linguistic issues, because if you select the slot value from the knowledge base, it will be always in one version. So you cannot have a language variability. And it needs high human effort for defining all the rules. So let's make a step forward, and we can think that it can be convenient to use a language model. So here I'm meaning a large language model, a pre-trained language model, such as Berton, the image refers to Berton, which is a very huge language model implemented by Google. So These language models are usually made by big companies because they need a very huge amount of data, and they know things. They have a very big knowledge about a lot of things. So we can just take them and use them for our situation. But let's say so. If we say that we use this model for predicting Trentino food, actually this is not feasible. It's not a real situation. Why is that? Well, simply because the language model doesn't have the information of your specific domain. Or better, it can have the information, but it has no clue of why it should predict Trentino rather than another type of food. So language model basically predicts the most likely word to fill that mask, and this regards the probability that it has based on the training data that is stored. So there's nothing telling him that he should predict Trentino food. So, but we can do something starting from this point. We can do, for example, what we call grounding. Grounding means that basically we first ask the model to predict the word, and as a post process, we do a sort of filter. So we look inside our knowledge base target, and we decide which information is relevant to our domain and which information is not. In this way, we are doing a sort of filter, and so we are selecting only the values that are relevant to our domain. And in this way, we can predict anything. This is a semi-controlled environment because on one side we are leaving the model free to predict whatever it wants. On the other side, we are filtering it in a subsequent process. And it also solves the linguistic issue because we can assume that the value predicted by the model is actually appropriate for that position in the sentence. On the other side, if we do grounding, we need to define some constraints by hand. So we need to define some rules to decide whether a value is appropriate or not for our domain. And also, we are assuming that the domain knowledge is contained in the language model, so that Trentino somewhere is already present in the large language model, and we need to filter it afterwards. Another way is prompting. So here also we are using a large language model, and we are assuming that the information is contained in the language model. But we are extracting the information that we want by means of a prompt. A prompt we can see it as a pattern. So we know that the domain is Trento, so we can create a prompt. I want a restaurant in Trento with mask type of food, and in this way we can force the language model to produce the value that we want. So we can imagine that the language model will produce Trentino food. Here we don't have any need of the knowledge base, we just need the prompt. And we can leverage at the maximum the knowledge that is contained in the language model. On the other side, also here we are assuming that the knowledge is contained in the language model, and we need to do prompt engineering. What does it mean? We need to decide which is the best prompt, because each prompt will give different results. So we need to make this choice. And finally, the fourth strategy is fine-tuning the language model. So here we are taking the same large language model, and now we are retraining this model on our domain. And this operation is called fine-tuning. And so once we have the fine-tuned language model, we can use this model to predict the word in the sentence. Here we solve the linguistic issues. We leverage both the language model knowledge and the domain knowledge. The con is that there is a certain cost of creating the patterns that are used for training the language model in fine-tuning. So this last strategy is the one we most focused on, and we are going to spend a couple more minutes on it. So this is the general functioning of fine-tuning, of the fine-tuning that we did. So it's divided into 3 steps, and we are going to see them one by one. So the first one is utterances creation. So we need to actually create the data that is used for doing the fine-tuning. And how do we do it? So we take all the conversational data set, the source data set, and we extract some sentences from this data set. Can be, for example, looking for a British food restaurant. Then we must British. And starting from this, we take our new domain knowledge. We look for all the restaurant foods that are in our domain knowledge. And we basically substitute each one of the foods with the mask. And in this way, you can create a very large number of similar sentences with different slot values. And then these sentences will go to populate the utterance, the new domain utterances. Now, these domain utterances are used for doing the fine-tuning. So we simply take the pre-trained language model, we give it the new domain utterances. Let's pretend it says triangle instead of pizza, and then we can fine-tune our model. Once we have the fine-tuned model, we can simply use this model for making the predictions. So we take all the sentences in the training dialogues. Again, we mask the slot value, but this time we are actually substituting the mask with the proper value that is produced by the fine-tuned language model. So the fine-tuned language model will produce a certain number of candidates, and with a certain probability, we select one of these candidates for making the substitution. Okay, so these are the results of this fine-tuning dialog adaptation. So we are showing the results for the dialog state tracking components. So the light orange and the light blue are the adapted, are the models that are trained on the adapted data sets. As you can see, there are massive improvements to the initial situation, the no adaptation situation, in particular with the trade model. So to conclude, we have seen that when we bring some changes to the world, this comes with huge degradations of model performances. And so we need some techniques for implementing dialog adaptation, so to create a new dialogues that are adapted to the new domain. We have seen some of these techniques. We have focused on the fine-tuned language model, and so fine-tuning a model for generating new slot values. And we have seen that this shows encouraging results. So in the future, we will explore more of these techniques, for example, generating the whole sentence and analyze the results, the outcomes that different strategies have on the impact of the main techniques. It was all. Thank you.